Okay, the accreted material clearly has a lot more angular momentum per unit mass than the white dwarf did. Why? Because as far as the white dwarf is concerned, this stuff is in orbit around it. So it clearly has a lot more angular momentum. So this material tends to spin up the white dwarf. So this is a way of taking a white dwarf star and turning it into a rapidly rotating white dwarf star. So as this accretion process goes on, the mass of the white dwarf goes up as this material builds up. Its angular momentum also goes up. And at some point, its mass will become so large that it can't support itself hydrodynamically. That is, the pressure that is keeping the white dwarf from collapsing, this electron degeneracy pressure, just isn't sufficient, and so it will collapse. Okay, so that's very much like this mechanism, but this is a way of producing a core which is almost guaranteed to be rather rapidly rotating to start with. Okay, up here, well, it's hard to get cores in the middle of stars to be rotating rapidly. If they were rotating rapidly, coupling between them and the outer part of the star would tend to slow them down. So even though you're guaranteed to have a big enhancement, this initial angular velocity might be pretty small. So you might not end up with a very large one. But in this accretion-induced collapse, you're almost guaranteed to have a pretty rapidly rotating initial core. The problem with this mechanism astrophysically is that most of the time when this collapse starts, in fact what you get is a nuclear detonation and it just blows itself up and you get no neutron star at all. But some fraction of the time people think that you do end up with a neutron star. I don't know what the fraction it is. It's a percent or a tenth of a percent or something like that. It's not the most likely outcome. But the ones you do get this way, the expectation is they will have high angular momentum and you'll have very rapidly rotating neutron stars produced in the process. Other possible mechanisms include things like you could have the same mechanism here, except you could have a neutron star in the middle and spin it up by accretion. So let's call this 3. Or another possibility is you can imagine having a couple of neutron stars which are in orbit around each other. The orbit decays because they emit gravitational radiation. Yes?
Just a nice question. When you feed stuff to a neutron star core, then the final object, will it be a neutron star, or will it be a star with a neutron star core and some hydrogen around it?
So it will be a neutron star with hydrogen around it, but now you can ask, say you built up a lot of material on the surface, how thick would this material have to be before the stuff at the bottom of this ocean starts burning into first higher nuclei and then eventually into neutrons? Yes, so it always does that. You always end up with an ocean of hydrogen on the surface, which is, I don't know, tens of meters thick or something like that. But below that, it looks just like a neutron star. The fraction of mass that's in the sort of the real neutron star part is some very large fraction. I don't remember how many nines in 99.99 it is, but it's some very large fraction.
So just a thin crust and that.
So you have a thin crust, and then on top of the crust you have a liquid hydrogen ocean, which it constitutes a very small fraction of the mass. So when the ocean gets too thick, then the material at the bottom burns and turns into heavier nuclei, and then that puts more pressure on the top of the crust, and the stuff on the bottom of the crust melts and turns into pure neutrons. So there's this whole processing of material through ocean crust and then down into the core as you accrete material.
By too thick, then just a few tens of meters.
Something like that, yeah. I don't remember exactly what the numbers are, but that's roughly the right length scale. So another possibility is you could have a couple of neutron stars, which clearly have lots of angular momentum. They in-spiral by emitting gravitational waves or something. Eventually, these things are going to coalesce and collide. Exactly what happens is completely unknown, I think, at this point. The whole thing could blow up. But one possibility is you could be left with some remnant which has a lot of angular momentum on the average, which is might be something like a rapidly rotating neutron star, and then a lot of garbage spewed out. Another possibility that they'll turn into a black hole and there won't be anything left, but at least one possibility is that you'll get a rapidly rotating neutron star out of that. Okay, so we think it's at least plausible that under some circumstances you'll get neutron stars. So that means we want to explore the possibility of having these dynamical instabilities in more realistic objects than these Maclaurin spheroids. So over the past, I don't know, 20 or 30 years, people have been doing a whole series of calculations in an attempt to do more realistic calculations of this sort. So let me just report on some of them. Lost my eraser again. Ah, there's another one back there. That's what I need. So the first thing that people studied is stars which are almost, or which are similar to Maclaurin spheroids in some sense. And the sense in which they were similar is that they assumed that the angular momentum distribution of the material inside the star was the same as that of the Maclaurin spheroid. So what do I mean by angular momentum distribution? So people define a function they call little j, which is the angular momentum per unit mass. So it's the square of the radial distance of that little element of fluid from the rotation axis times the angular velocity at that point. And this angular velocity may depend on radius. Okay, so inside a Maclaurin spheroid, you can calculate what this is. Well, it's simple. Omega is a constant, and it just goes like r or omega squared. So this is the function that they have in mind, but they think about it in the following way. So you can imagine taking a large star, which you could crudely approximate as a Maclaurin spheroid, and then imagine that it collapses down after going through one of these accretion-induced collapse, or maybe it's a collapse of a core. So how do you translate this angular momentum law into the angular momentum law that results after this collapse has proceeded? Okay, so you can imagine having this initial rotating star, and it eventually collapses down into some smaller and presumably more rapidly rotating configuration. Well, as the collapse proceeds, you can imagine having a cylinder of material here, which contains some fraction of the mass. Let me call little m the fraction of the mass contained inside of this cylinder. And then as the star collapsed, you could map this into some much smaller cylinder, which contains the same fraction of mass as this guy. Okay, so this cylinder of material gets put into that cylinder. And similarly, you could do that with other cylinders get mapped into, say, that cylinder. So you could consider this angular momentum function to be a function of this mass fraction. And if the angular momentum of each little particle is conserved during this collapse process, then this j of m function in the initial star should be the same as the j of m function in the final star. Okay, because each of these cylinders gets mapped into the corresponding cylinder here. That is, this particle on the surface of this guy, that is on the cylinder that has a fraction of the mass inside of little m, would also be on the surface of the cylinder containing the mass containing the mass fraction m. And if you want the angular momentum of this particle to be the same as the angular momentum of the initial particle, that means that this function j of m ought to be the same in the two configurations. So people have looked at stars which are like neutron stars, but which in fact have this angular momentum distribution j of m given by this Maclaurin spheroid law. Okay, so a whole bunch of numerical work of this sort has been done. And what people have found is that the place where dynamical instability occurs is almost the same as in the Maclaurin spheroid case. Okay, so let me write down that result. Okay, neutron stars. Having McLaurin Okay, so if you build these other stars, and in general, in the McLaurin spheroid, this J of M came from this rigidly rotating configuration. When this collapse process happens, in order to conserve angular momentum, this omega has to turn into something which has differential rotation. That is, omega depends strongly on the radius inside the star. But if it has the same J of M as McLaurin, then they find that the place where dynamical instability sets in is almost the same, to within a percent or so. Let me show you some recent work. This comes from Kim New, Johnson Trellin, and Joel Tolene looked at a bunch of models of this sort. They looked at stars where the equation of state for the material, the pressure is proportional to the density to the 5/3 power. This top graph shows what the shape, so this is the z-axis, that's the rotation axis. This is this pomega, this radial, the cylindrical radial coordinate, and these surfaces show what the contours of constant density surfaces look like in this star. So this is a very rapidly rotating, very flattened star. This star has a beta of 0.298. These bottom graphs, this shows how the density changes as you move out along the equatorial plane. Rho over the central density looks like that, and the angular velocity is this dashed curve. So they studied dynamical instability of these kinds of objects, and they found that for betas greater than about 0.27, they were dynamically unstable. For betas less than about 0.27, they were not. The other thing they were interested in is actually following the evolution of the instability and seeing what the star looked like as it evolved. So here are some pictures. This is looking down on the rotation axis. So the star is initially axisymmetric at time t equals 0. As time evolves, it deforms itself into this ellipsoidal shape, similar to what the McLaurin spheroids look like. So this instability people call the bar mode instability, because the axisymmetric shape gets deformed into something like a bar. But then as this evolves, you get this sort of backward trailing spiral behavior like you see in galaxies. And here's a sequence of snapshots of what the densities look like as a function of time. The thing they were interested in, particularly in this recent paper, there had been some reports that said that yes, you can form a dynamical instability of this sort, but it only lasts for a few cycles, and then hydrodynamic processes actually suppress it, and that you really wouldn't get very much gravitational radiation out. And what they showed in their numerical work, using a couple of different types of hydrodynamic codes, is that at least for some class of models, this class that they studied, in fact, you do get long-lived instabilities that have many, many cycles that would be capable of producing gravitational radiation for a long time, and therefore you could extract a lot of angular momentum and energy in gravitational waves from this kind of mechanism. Okay, so that's one somewhat more realistic than McLaurin set of studies that have been done, and they basically verified this McLaurin value for beta. More recently, Yuk-Pung Liu, who is a grad student here, has been looking at an even more realistic set of models. Instead of taking the Maclaurin spheroid distribution of this J, which is just a rigid rotation, he uses the angular momentum distribution that you get by solving the equations for the structure of accurate white dwarf models. He's thinking in terms of this accretion-induced collapse model, where you have a very rapidly rotating white dwarf here, which has been spun up by accretion. So this white dwarf isn't uniform density. It's in fact has a very high central density compared to the density at the outer edge of the star. And so its angular momentum distribution is rather different than that of the Maclaurin spheroids. And so he was interested in asking, under these more realistic configurations where you have a different differential rotation law, the one you would expect to be closer to what you see in an actual collapse, do you still get dynamical instabilities? And if so, how fast does the star have to be rotating? So here is the angular momentum law that Yuk-Tung derived. So it's basically this m omega squared, and then he's made it dimensionless by multiplying by the total mass of the star and dividing by J. So this is now a dimensionless number. And this J is a function of this little m, which is the mass fraction inside a certain radius, and this is what it looks like. So it's some curve which is actually very sharply peaked near the surface of the star. He then used this angular momentum distribution to construct neutron stars using, instead of these artificial polytropic equations of state, he used some equations of state that you get by doing nuclear physics and actually calculating what the density and pressure should be like. And these neutron stars that he gets have this interesting structure. So here is Z, the rotation axis, and this is omega, this cylindrical rotation axis. So you have to think of these as being rotated around this C axis. There is this huge envelope. This thing is, 1,000 kilometers. That's the size of the white dwarf that you made it out of, basically. And then hidden down in the middle here, here's a blow-up of this inner region. There is the thing that you would really think of as the neutron star. So this thing is about 10 or 20 kilometers, and the density in this region is typical neutron star densities. This outer material is just very low density material that got hung up by centrifugal forces. It was trying to collapse, but it just had too much angular momentum. It couldn't go in any farther than what its Keplerian orbital angular velocity would allow it to, basically. And so you get a small fraction of the mass is hung up in this huge envelope, and then down in the core you get something which is much more like a neutron star, but it's quite flattened. It's rotating very rapidly. He studied the dynamical instability of these objects. So let me show you another graph of some of the properties of these things. On the left, this is the angular velocity as a function of radius for a whole series of models that he computed. So this is the angular velocity on the rotation axis, and some of these it gets larger as you go out, and then in the outer layer it falls off like 1 over r to the 3/2. That's just the Keplerian angular velocity law that corresponds to that big tail. And this graph shows this parameter beta as a function of radius in these stars. So it always starts out 0, but in the more rapidly rotating ones, it gets up to about 0.26, I think is the biggest one that he found. So this sounds a little bad, because if we think that the critical beta is 0.27, then it's possible that you just can't form objects which rotate rapidly enough to have dynamical instabilities. So Yuk-Tung studied the stability of these objects. I'm getting all messed up here. And he found that, in fact, some of these objects, the most rapidly rotating ones, are dynamically unstable. So this is the sort of classic result, and blue, so using realistic rotation laws. and realistic equation of state, that is, the equation that tells you how the density depends on the pressure, found that you have dynamical instabilities for beta greater than about 0.24 up to about 0.25, depending on exactly which set of models he was looking at. So you can make models which rotate up to about 0.26 using this set of models that he was looking at, and so the very most rapidly rotating ones do have dynamical instabilities, and he estimated that the gravitational radiation from them might be detectable by LIGO 2 for sources out, I don't remember what the characteristic distance, it was tens of megaparsecs. Okay, so that's one class of making the calculation more realistic that people have done. Another class is that we know that real neutron stars have fairly strong gravitational fields. Right? All of these calculations so far have been done with Newtonian hydrodynamics and Newtonian gravity, so you might think that would make a big difference. So the first calculations to do this properly using relativistic gravity, relativistic hydrodynamics, was done by Stu Shapiro, Masaru Shibata, and colleagues. So let me show some of their results. Okay. So this is a graph of this beta, this measure of the rotational rate that everyone uses. And this axis shows m over r. Okay, so these are the m over r's for the neutron stars. So for very Newtonian stars, we know that the ratio of m over r is a very small number, right? And the limit of a star like the sun, this is almost 0, like 10 to the minus 5 or something. For a neutron star, this number can get up to about 0.2, 0.1 or so. So what they did is they studied neutron stars having different values of m over r and then determined whether they were dynamically stable or not. And this bottom curve shows, let's see, these are the curves with m over r 0.5, so they correspond to these for stellar models. And these correspond to the different values of beta. So this one is what they got by evolving a neutron star with this top value of beta, and you can see it evolved into something that basically looks like a binary. This one comes with a slightly smaller beta, this one is this triangle, and then this bottom one is in fact stable. They evolved it and it just stayed axisymmetric no matter what happened. So in these graphs up here, the solid circles, or actually all the circles, correspond to models that they evolved in which nothing happened. They just stayed axisymmetric like this. And all of these triangles are models that they evolved which developed these bar mode kind of instabilities. And you see that for very relativistic models, these guys up here, they found instabilities with betas down closer to about 0.25. Here's one, about 0.25. They clearly haven't computed very many models. These were done using very expensive 3D hydro codes. But the trend is that as you make things more relativistic, the dynamical instability seems to set in for lower values of beta. Now, I'm not sure exactly what that means. Yuk-Tung Liu has been looking at the same kind of issue recently in the post-Newtonian context. And one of the ambiguities that he's been faced with is when you compare a Newtonian star, something down here at m over r is 0, with one of these relativistic stars, what value of beta on the relativistic star corresponds to the same star? Right, so even though these betas appear to be getting smaller for the dynamical instability, if you're supposed to compare this one with that guy, then it isn't very impressive. And so I don't think Shapiro and these guys have really sorted that out very clearly. I'm not quite sure what they're comparing. So Yuktung is in the middle of trying to sort that all out at the moment. Point is, there's a lot of work to be done, but the preliminary indications are that relativity helps you, that it tends to make things more unstable.
Would it be plausible to see a neutron-star binary that coalesced, separated, coalesced, separated? That would be a nice way for them to move forward.
Yeah, that would be a great thing to look for. Do I think it's plausible? No. But if you see one, I'm happy to hear about it. Yeah, I mean,
Barely coalescing.
yeah, and then some kind of instability setting in. I mean, the time scale for this to happen is really quick. Remember, the sort of hydrodynamic time scale here is milliseconds, or fraction of milliseconds. So the time between this thing forming and then this thing coming apart again and then in-spiraling it would be fractions of a second. So I'm not sure that you would really distinguish this intermediate phase as being anything particularly distinct. It would be just, you know, part of the well, noise of the signal, of the science coming out as this thing flies apart.
It's also worth noting that if the gravitational waves come out at something like millisecond periods, we've got problems because the LIGO sensitivity goes somewhat worse in the vicinity of a kilohertz due to shock noise, which we'll discuss next term. And so one wants to hope that some of the action is down below a kilohertz or periods longer than milliseconds.
Okay, so let me tell you about a couple of other things that have been going on recently that I really don't understand. They seem very strange to me, but they're kind of enticing. So a couple of groups have started looking at other angular momentum distributions. So the things that have been looked at up till now are this Maclaurin spheroid angular momentum distribution, which I don't think anybody believes is particularly significant astrophysically. And then Yuktung has made an attempt to do an honest guess of what the most plausible thing you might expect, and found that things were slightly more unstable. But a number of groups have been just exploring, well, what happens if you change the angular momentum distribution in some bizarre way? Okay, so one of the, I guess the first result, Joan Centrella and some of her colleagues have looked at angular velocity distributions that have the following form. Okay, so these have the property that they depend on the radial distance from the rotation axis. As omega goes to 0, the angular velocity on the axis is just this constant omega 0. And then as omega goes away from the axis, this denominator grows quadratically. And they've expressed it as a ratio. This is the radius of the star in the equatorial direction. So this ratio goes to 1 on the surface of the star at the equator. And then there's some huge factor here. Okay, so as you get to the outer layers of the star, this angular velocity is dropping like 1 over omega squared. Okay, so they studied, let's see, they looked at stars with this equation of state. And they studied the dynamical instability of those stars. And what they found, well, let me show you some pictures of the stars first. Okay, so the rotation axis goes up and this omega direction goes this way, and so you should think of these as being axisymmetric around an axis. So for T over W is 0.18, this thing looks like a lifesaver. Okay, so there are actually maximum density, there's a torus of maximum density material. For slightly lower material, it's a little bit less of a lozenge, and down to about 0.9. Okay, so these are the objects that they study when they build them with this rotation law. And they find that these guys are dynamically unstable for beta greater than 0.14. Okay, so that's like half of the standard Maclaurin value. So that's really interesting, but the question is, is this remotely like anything you would actually get in astrophysics? Why this rotation law? So nobody, as far as I know, has any plausible reason for believing that that's realistic. And then very, very recently, when I was in Tokyo last month, I got a preprint from Masaru Shibata and his group, who have been looking at similar things. And they've looked at objects that have the following rotation law. It's similar to that one. In fact, it's not quite as extreme. Okay, so again, it has this omega over r squared, and they choose a constant which is about 11. But they look at a somewhat more realistic, for a neutron star point of view, equation of state. The pressure is proportional to the density squared. It turns out that this is a pretty good model of what real nuclear matter looks like. You just take the equations of state that you find in the literature where people have done nuclear physics properly, then p equals rho squared is not a bad approximation to it. 4/3 is not so good for neutron stars. But they find something even more shocking. They find dynamical instability. I'll show you some pictures of this in a minute. For beta greater than 0.04. Okay, so let me show you some pictures of their results. So this first graph, they did the calculation two ways. This is work of Masaru Shibata and Araguchi and one of their grad students, Carino. Shibata has a 3D nonlinear hydrodynamic code, and so they just took these very rapidly rotating configurations, put them in his code, and let it rip. And these wiggly lines are a measure of the non-axisymmetric. This eta is the difference between the moment of inertias around the x-axis and the y-axis, normalized by their average value. So if it were axisymmetric, those two would be equal, and that eta would be 0. If it's non-axisymmetric, then this is basically proportional to the centricity of the ellipse that it would be deformed to. So that's the parameter that they use. And they find that this quantity grows exponentially for the first part of the evolution until its value reaches about 1/10, which is pretty big. So this is quite a significant deformation. And then he gets nonlinear saturation. It sort of oscillates around. These are for 3 different models. This is for a beta of 0.13, this is 0.08, and this is 0.04. So in all 3 cases, this grows to saturation strength. So this was done with Shibata's code, and then Araguchi is very good at doing linear perturbation theory, and he had a linearized perturbation code in which he verified the results and got essentially the same numbers. Let me show you a graph that they have in their preprint, which shows these are the real and the imaginary parts of the frequencies of the mode that they saw as a function of beta. The dots are from Shibata's nonlinear hydro code, and the solid curve is from Araguchi's linearized perturbation theory. So these are the real parts of the frequencies in some essentially arbitrary units. Here we have the imaginary parts of the frequencies, and in fact you can see that for models down to beta of 0.04, they both get dynamically unstable modes, and then the value of this imaginary part grows as beta grows. Presumably, this imaginary part goes to 0 at some point down in about 0.03 or something. You can read off the graph. So again, I don't know what this means. What it means is that, at least in principle, you can have fairly slowly rotating configurations with dynamical instabilities. I'm very skeptical about whether objects like this actually form in astrophysics. That remains to be seen. They certainly don't have a justification for that in their paper. So you had a question?
What's the motivation for choosing coefficients of order 11 or 25 in the denominator? Do they justify it?
No. I mean, the justification is because they found something interesting, right? So, yeah, so I don't think there is a justification.
So, do the Shibata equilibria that are unstable all have this ring-like central density?
I don't know.
In some sense, it's like perturbing a torus.
Right. I mean, these are not as extreme as centrellas are much worse than this. So I don't know that quite. This is a graph which shows, looking down the rotation axis, these are constant density surfaces in the initial configuration, and then this is what it evolves to when the mode is fully grown, but this doesn't really show whether it's got a toroidal instability or not. However, I must say that if you look at, so I'm out of time, I'm sorry. The right thing to do next, and people are just starting to do it, is to really use 3D hydrodynamic codes to start with something like one of these accreting white dwarfs and let it collapse and just see what happens, right? Just determine what the rotation rate really is, but really do it dynamically in the computer rather than doing it in this sort of quasi-equilibrium model approach that everyone has used so far. And there's starting to be some work of this sort. In fact, I won't comment very much on it. I picked one paper out of the literature. This is some work done by the Garshing group, Muller, Rufert, and Ramp. These graphs, so they take an initial rotating configuration, they just let it do hydrodynamic collapse, and they just follow and see what happens. If it's unstable, it'll show up in the code. So this is a graph as a function of time in their evolution. This shows this beta parameter. They did 3 different runs, and you can see that in their runs, beta crosses this 0.27 curve for a brief period of time, but then the model bounces back out, and it ends up sort of more slowly rotating. So there's about a few these are time in milliseconds, where the beta is big enough to have a dynamical instability. And this graph shows the density, the central density of this object as it evolves. And again, at the same time, at about 30 milliseconds, for a few milliseconds, there's a big spike in the density, but this is only a little over 10 to the 14th grams per cubic centimeter, which is pretty low density for a typical neutron star. Typical non-rotating neutron star has a central density of more like 10 to the 15th. So this is quite low density. And then it blows itself back out, and the central density goes down to, again, a smaller value. They studied the evolution of this object. So let me just show the evolution of one of these runs. Pardon? Okay, this is it. Starts, turns into an interesting propeller looking, it's an m=3 dynamical instability, but it only lasts about 3 milliseconds, and then it goes stable again. So I think there's an open question of whether these dynamical instabilities really happen, and what we need is a bunch of people doing high quality 3D numerical hydrodynamics to figure it out for us. Anyway, thank you.